In this video, we are going to continue looking at periodicity and the trends in the periodic table. Let's start by looking at periodicity in the formula of halides. What are halides? Halides are ionic salts formed from the reaction of halogens with metals. Remember that halogens are your group 7 or group 17 elements like fluorine, chlorine, bromine, and iodine. So halogens react easily with other metals because they do not have a filled outermost energy level. The ratio in which the halide ions combine with metal ions will depend on the valency of the metal that the halogen reacts with. Say, for example, a halogen reacts with a metal in group 1. So the compound will be MX, for example. If it reacts with lithium, let's say chlorine reacts with lithium, the formula will be LiCl, lithium chloride. But if a halogen reacts with a group 2 element, a metal in group 2, then the formula will be NX2. So the halogen will take the group number of the valency of the metal. And for example, if chlorine reacts with beryllium, it's going to be BeCl2. And if a halogen again reacts with a group 3 metal element, the formula will be MX3, with the halogen taking the valency of the metal, which in this case is 3. If aluminium reacts with fluorine, which is a halogen, then the formula will be AlF3. And then you have other examples as well. Now let us look at the periodicity in the formula of oxides. So oxides are compounds formed when oxygen reacts with metals. So remember that the valency of oxygen is -2. And so if oxygen reacts with a group 1 metal, the compound formula will be M2O. So remember, when you use the crossover method that I taught you to use when you are writing the formula in case you are given a name. So I taught you the crossover method. You use it here when oxygen reacts with a group 1 metal. The formula will be M2O. For example, when it reacts with lithium, the formula will be Li2O. And then if oxygen reacts with a group 2 metal, again you are going to use the crossover method, and you are going to get a formula of MO. For example, if it reacts with magnesium, the formula will be MgO. And then if it reacts with a group 3 metal, the formula will be Al2O3, which again you get from using the crossover method. Let us continue with the trends in the periodic table. Now we are going to look at ionization energy, electron affinity, and electronegativity. Let us start looking at the ionization energy. When an atom loses an electron or electrons, a positive ion will be formed. This makes sense because if it loses an electron is a negative charge or a negative ion. So if it loses the negative ion, then it's going to have more positive charges than negative charges. This will only happen if we have enough energy to remove the electron from the atom. And the ionization energy is an indication of how strongly an electron is bonded to the atom. So it makes sense that if the bonding force is much more stronger, then you will require more energy to remove electrons from the atoms of that element. So your ionization energy will be higher too. I said earlier that there is first ionization energy, second ionization energy, third ionization energy. The first ionization energy is the energy that we require to free the first electron from a neutral atom. So we start removing electrons from the outermost energy level. We start removing electrons from the valence electron. So then the electron furthest from the nucleus will have the highest energy and will be removed first. As you can see here, the trends in ionization energy. As you go down the group, your ionization energy increases, and as you move from left to right in the periodic table, your ionization energy increases. We're going to see on the next slide the reasons for these trends. Let's start by looking at the trends in the periods. So as you move from left to right in the period, so as you move from hydrogen to helium, lithium to neon, sodium to argon, etc., your ionization energy increases. What is the reason for this? The reason is that the number of protons in the nucleus of the atom increases as you move from left to right in the periodic table. So that is the nuclear charge. So the nuclear charge increases, and at the same time the radius of the atom decreases. So remember, when we did atomic radius, we said that as you move from left to right in the periodic table, the atomic radius decreases, and so your attractive forces will be greater. So you will need a higher ionization energy to remove the electron. Another trend that we see in the period is that the noble gases have very high ionization energies. What could be the reason for this? The reason is that the outer energy levels of these elements are completely filled with electrons, which makes it harder to remove electrons. So if you have a fully filled or a completely filled energy level, then it will be harder to remove electrons from that filled energy level. So that is why noble gases have very high ionization energy. The deviations in the period. We have two deviations in the period. So when we move from beryllium to boron and from magnesium to aluminium, there is an unexpected decrease in ionization energy. We know that when we move from beryllium to boron, we should see an increase, but we see a decrease. What is the reason for that? It is because boron's outermost electron is in a 2p sublevel, which is further from the nucleus. So it has a higher energy than that of the 2s sublevel of beryllium atom. As you can see, the electron configurations of both beryllium and boron, beryllium ends at 2s at the s orbital, and boron ends at the p orbital. So it is much more easier to remove the electron for boron than to remove the electron in beryllium, because the electron in boron is much more farther away from the nucleus compared to the electron of the beryllium. So the electron of the beryllium is much more closer to the nucleus. So the shielding of the beryllium of the beryllium electron is much more weaker than the shielding of the boron electron. So the boron electron is much more shielded compared to the beryllium electron. So it is much more easier to remove an electron in boron than to remove an electron in beryllium. And we have another deviation from nitrogen to oxygen and from phosphorus to sulfur. And we see a decrease instead of an increase. And why is that? It is because the oxygen atom has a 2p orbital with an electron pair. If you look at these Aufbau diagrams for both oxygen and nitrogen, you can see that. So the paired electrons, they repel each other, and so we need less energy to remove these paired electrons, and so the same applies for phosphorus and sulfur. Trends in groups. As we move down a group, the ionization energy decreases. So as you move from the top of the group to the bottom of the group, you get a decrease in ionization energy. Why is that? It is because as you move from the top to the bottom of the group, you add a new outer energy level each time you move from group 1 to group 2 to you add a new energy level as you move down. So this means that, as you can see in the three diagrams, the outermost energy level of potassium is much more farther from the nucleus compared to the outermost energy level of lithium. So it is much more easier to remove electrons from potassium than to remove electrons from lithium, because the electrons from the outer electrons of lithium are not shielded compared to the outermost energy levels of potassium. Let's move on to electron affinity. Electron affinity is the change in energy that takes place when a neutral atom in the gaseous state accepts an electron to form an anion. And usually electron affinity is energy that is being released. And the greater the electron affinity of an element is, the greater the chance that such an atom will accept an electron during a chemical reaction. Let us look at the trends then. As we move across the period, we see an increase in the electron affinity. Therefore, the nonmetals will have higher electron affinity values compared to the metals. Remember, the metals, we find them on the left of the periodic table, and the nonmetals are on the right of the periodic table. The reason for this is because there is a decrease in atomic radius and increase in nuclear charge as you move from left to right. So the nonmetal atoms are short of only a few electrons to attain a stable noble gas structure, and thus they are ready to accept electrons. So for example, oxygen, it just needs 2 electrons to be able to fill its outermost energy level. So then it makes sense that oxygen will have a higher electron affinity, because it is ready to accept electrons, because it is just short of 2 electrons to fill its outermost energy level. And also fluorine, for example, or chlorine, they also just need 1 to fill their outermost energy level. So it makes sense that they have a higher electron affinity. And then the noble gases, they have low electron affinity values. Why is that? It is because they do not want to accept electrons since they already have a full outer energy level. So since they already have a completely filled outer energy level, they do not want to accept any electrons. So their electron affinity is very, very low. That is why we see a drop from fluorine to neon and chlorine to argon. Let's move to electronegativity. Electronegativity indicates how strongly an atom of the element in a compound attracts a shared electron pair. It can be determined in comparison with that of another element and is therefore a relative value. Let us look at the trends in electronegativity. As we move across the period from left to right, we see an increase in electronegativity, which means that fluorine will have the smallest atomic radius and largest electronegativity. What is the reason for this? The reason for this is that the electronegativity values are directly related to the electron configuration of the atoms of an element, and during bonding, the atoms involved strive to attain a full outer energy level. Remember, I told you that when elements react, those that are short of a few electrons, they want to strive to fill their outer energy level by accepting electrons, and those that need a lot of electrons to fill their outermost energy level, they want to lose their electrons. This means that the nonmetals to the right of the table are more inclined to accept electrons, like I said, like your oxygen, like your nitrogen and chlorine, and exert a stronger force of attraction on a shared electron pair. The metals on the left are more inclined to donate electrons, like your sodium, and exert a weaker force of attraction on an electron pair, so they have a lower electronegativity. Another trend that we see is in a group. So the electronegativity of the elements decreases as you move from up to the bottom of the group. The reason for this is that as you go down a group, the atom acquires a new outer energy level. So we have greater shielding by the inner electron. So shielding, just remember the circle of dancing people that I made example of earlier. So as you add more outer energy levels, you get more shielding by the inner electrons, and the force of attraction of the nucleus on each shared electron pair decreases. That is it on this video. On the next video, we will look at the reactivity of the different elements in groups 1, 2, 7, and 8.